Okay, let's go ahead and get started. Our question of the day had to do with different kinds of dives, pretty equally split there between skydiving and scuba diving. They keep cutting me off right at 50 minutes, which is probably good, but there was something I wanted to mention at the very end last time that I got cut off. I didn't quite have a chance. I said it briefly, but let me spend a little more time about it. So the version of ArrayIntList that was posted on the calendar for Monday, and that's described in the notes for that day, instead of checking for capacity and throwing an exception, so that's what the other version did, is that if you had 100 things in the structure, and you have a capacity of 100, if you add anything beyond 100, it throws an exception. Well, that's not what the built-in ArrayList does, and that's not what the version that I put on the calendar for Monday does. So let me say a little bit about it. It's an interesting detail about how ArrayList works, something that particularly I think computer scientists might find interesting. Maybe the rest of you will find it less interesting, but the future computer scientists in the audience might find this interesting. So the question is, if you want to set this up in such a way that when you run out of space, you make more space, there are different kinds of approaches you can take. The original Java class libraries had something called vector, and vector was like the first attempt to do ArrayList, and it was done badly. One of the things that vector does is that if you run out of space, it makes bigger, it kind of adds space. It makes a new array, copies things over, but it adds some fixed size to it, like it adds an extra 100 elements. I mean, that's okay when you've got 100 things, then it adds 100, it adds 100, it adds 100. It works okay for a while, but when you get up to something like having 1,000,000 things in the structure, then it only adds an extra 100, which is a tiny little bit extra to add. And if you're doing that many things, you're likely to get a lot bigger than 1,000,000. So, it adds 100 at a time, copying over all 1,000,000 things each time. That's very expensive. We're going to talk about this in a later lecture, but we would call that an O of n squared solution. It's a bad solution. They screwed up, in doing vector. Well, that's partly why they did ArrayList, is they wanted it to be better. So what do we do instead? So if you run out of space, what you do is make a brand new array, and in the case of the code that this one uses, it doubles the size. And it adds one just in case the length was 0, but basically it's doubling. So like if you had 100 things, it makes it 200. It goes from 200 to 400, 400 to 800, and so forth. So always doubling. Now, if you think about it, like suppose it had been 1,000, and you added 1,001st element. Well, then it's got to do this task of doubling, which is expensive. It's got to make an array that's 2,000 long. It has to copy over the 1,000 things that were in the old array, and it has to set the other 1,000 things to 0. So that's 2,000 things it has to do on that call for add. So that's an expensive call on add, but that allows you to have another 999 calls that are not going to require that. So there's basically, 1,000 calls in a row. You're going to be able to do add, and you'll have enough room to do it. So you kind of spread out the cost. You spread out the 2,000 operations over those 1,000 adds you're able to do. And we say that the amortized cost, the spread out cost, is very cheap. It's 2 operations each, when you spread it out over those 1,000 adds. That word amortized is also used when people talk about mortgages, that you get a 30-year mortgage to spread it out over a long period of time. So that's what we get by the doubling. If you look at the internal documentation for ArrayList, it says in here, size is empty, these things run in constant time. The add operation runs in amortized constant time. That is, adding n elements requires O of n time. So they document that fact, that's how they do it. They don't tell you that they do doubling. They don't actually do doubling. They multiply by 1.5. So it's 50% increase instead of 100% increase. But that's what they do, and that's what they mean when they're talking here about an amortized cost. All right, anyway, that's kind of maybe more of interest to the computer science folks in the audience, our future computer scientists. I want to switch gears today, so let me kind of go over to this file over here that I've set up to work with. We've been talking about abstraction, and I didn't mention this before, but in the 142 class, I would say that what we were doing was control abstraction. Abstraction that has to do with the flow of control in a program. Our primary way of doing that was with methods. That basically we can think of the program as being broken down into 6 different distinct methods, for example. And so instead of thinking of all of that detail, you remember we didn't want to have lots of detail in main, we wanted to break it up into methods. So that was kind of what we were doing in 142. What we're doing here is more what would be called data abstraction. We're doing abstraction with data structures. A lot of people titled this course data structures, or data abstraction. So anyway, we're continuing in that vein. It's worth understanding that we've been talking about this for decades, from the beginning of time, just about, when computer science was first coming about. We had the notion of what are known as ADTs, abstract data types. So this was kind of a concept that was used early on because you have these different programming languages and they offer you different kinds of structures, and it just seemed like what was emerging is that people had in mind, for example, that there is a list-like structure, and we had a sense of what a list involves. It's an ordered sequence of values. We had in mind a set of operations that could be performed on a list versus, say, for example, a set. You were looking at that in a section yesterday. So lists versus sets is an example of 2 different ADTs. Now, a nice thing about Java is that Java gave us support for this with interfaces. So in Java, we're allowed to declare something that's actually part of the Java code we're writing, which is to have, say, a list interface or a set interface. So that's nice, is that Java actually makes it possible for us to do something a little more concrete, with this idea. Well, today what we're going to be talking about is 2 other ADTs, classic ADTs, what are known as stacks and what are known as queues. Now, it's going to seem weird because we talked about lists and sets, and now we're going to talk about stacks and queues. So a list can do everything that a stack can do and more. A list can do everything a queue can do and more. So stacks and queues are simpler than lists. So it seems a little odd to kind of backtrack and talk about a simpler structure, but there's various reasons why we want you to understand stacks and queues. Probably the most important reason is just that it's part of the culture and vocabulary of computer programming. So if you took an interview with a company and they said something like, I want you to work on this problem, I'm gonna give you a stack and I want you to do this with a stack. And you say, what's a stack? They're going to say, where did you learn computer science? So this is terminology you should be familiar with, stacks and queues. And maybe I'll say the following about it, that what we do with stacks and queues is not only do we deal with these simpler structures, but we even limit what you can do with these simple structures. We give you a very limited set of operations we want you to work with. And I guess what I would say is that I think that that's a good experience to have. It's a useful experience to have, to kind of practice working with a data structure where you don't have quite as many options available to you as you would, say, with a list structure. There's even other reasons, but anyway, that's enough kind of description of why. There's some terminology that you always have to talk about when you're doing stacks and queues. You have to talk about what's known as FIFO and what's known as LIFO. I can tell you that I only use FIFO and LIFO in this one lecture where I introduce stacks and queues, so I don't use this terminology otherwise. But anyway, it's worth knowing about this. First in, first out is the FIFO acronym. Last in, first out is the LIFO acronym. So what would that mean, first in, first out? Well, if you have the first in, first out, approach, that's a queue. So that leads to this structure that we call a queue. So I have a little short description here of the operations I want you to be able to perform on a queue. And so I mentioned that for Q of E, and Q is an interface, so this was kind of done the right way. There's a Q of E interface, but remember, interfaces aren't implementations, so that means that you have to have some specific concrete type, and we're going to use linked list of E. So we haven't talked about how that's implemented, but you don't need to know that. I mean, you just need to know that when you go to construct a Q, you'll make a new linked list. That's the kind of the concrete implementation that we're using for it. And there are 4 operations that we're going to be using for these Q structures. It's a linear structure like a list, so things can be added and removed from it. In classic Q terminology, these are sometimes referred to as NQ and DQ, but Java chose to just use add and remove. So we add to a queue, we can remove from a queue. There's a Boolean method that lets you know whether or not it's empty. Actually, just those 3 alone would be enough, because you could compute everything from there. But size is pretty convenient, so we let you use size as well. Now, what we're going to be doing with stacks and queues is your homework 2 is going to give you a little bit of practice with this, not a lot. Homework 2 is really more about something else, and I'll talk about that in Friday's lecture. Friday's going to be a lot about homework 2. So you get a tiny bit of practice with queues in working on homework 2. But the real place where this shows up is on the midterm, and so it's going to be less scary or relevant to you guys this quarter, since you're not going to have a proctored midterm. But in any event, on the midterm, I include a 25-point question. So it's the highest point value question on the midterm, to do a stack queue problem, to solve a stack queue problem. And for those problems, I limit you to the set of operations that are on kind of this short list here. In section tomorrow, the TAs are going to show you some of these old exam questions, and they'll give you their own way of understanding stacks and queues, the pictures they draw, and so forth. So you get to have some practice with it in section tomorrow. And as I say, it'll be on the midterm. I'm going to want you to do a sample midterm, so you'll have a chance to practice it there. There's one extra method that I'll talk about in Friday's lecture that I'm going to have you use for the homework. So there's one extra one that you can do on the homework, but not on the exam question. So I'll save that for Friday. And let me also just say that it would work to make a for each loop or to make an iterator, for a queue, but you're not allowed to. So that would be an example, because a for each loop is just not very queue-like. Queues, you're not supposed to be accessing things in the middle. Queues, you can add something to the queue, remove something from the queue, but not deal with the middle directly. So for queues, the analogy that I use for this is it's like standing in line. In fact, the British use the word queue the way we use the word line. You queue up, you go to the back of the queue. So, I think about something like a store where people need to check out. They've got merchandise that they want to buy, and there's a line of customers. I guess actually maybe you'd understand it more this way. There's like a checker here, and then there's this line of people who are waiting to check out. And so what do you do when you stand in line? That whoever got in line first is going to be the first customer who is helped by this cashier. That's the first in, first out. And so, I kind of think of queues in a horizontal way. So I think of kind of things being added in this way. And so things get added at the end. If someone comes along and they get at the front of the line, you're not allowed to do that, no cutting in line. Or if they tried to go in the middle, no, you're not allowed to access the middle of the line. Go to the back of the line. So you get added at the back of the line and you get removed from the front of the line. When the cashier says next, it's whoever's at the front of the line who's going to be the customer that's helped. So I kind of think of it as a horizontal structure where something's happening at each end of the structure. So things are being added at the end and things are being removed at the front. So kind of both ends of the structure are in play for a queue. For a stack, I kind of think about cafeteria trays, is the analogy maybe it's just because I went to a lot of cafeterias, in my lifetime, but they tend to have these dispensers in a cafeteria, where, spring-loaded thing where you could have a whole bunch of trays, in this cart, for trays. And so, imagine, for example, that there's, 20 trays that are in this structure. And if somebody from the kitchen comes and brings 5 clean trays, do they feel the need to lift up the 20 trays to put the 5 underneath? No, why bother? They just put it on top. They push on top is the terminology that we use for that. Let me show you what the stack description is. So instead of add and remove, we push onto a stack and we pop the top of a stack. Stack is an older structure. It was kind of done before Joshua Block arrived at Sun Microsystems. And so it was done the bad way. Stack is a class. There isn't a separate interface. So you'll say stack and you'll say stack because there isn't an interface that's separate from the implementation. I used to have people use my version of a stack that was done the right way, but I got convinced that it's better to have you use standard Java. So, this is a place where they kind of blew it, but all right, we can live with that. Stack is there isn't a separate interface, stack and stack. And it's the same kind of operations. To put something into the stack, you push something on top of this bunch of trays. So if I had a new tray, I'd push it on top. Another one, I'd push it on top. Another one, I'd push it on top. And then when you go to get a tray, you don't say, well, let me take the one at the bottom. You pop the stack. You pop one off the top and say, I'll take that one. And then another person comes and takes the next one. So you push and you pop, you push and you pop. And so it's always at one end of the structure. So, and I tend to think of this in a vertical way. So that's kind of my way of thinking of it, is I think about kind of these trays where you would push, 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 kind of the stack is getting taller, pop, 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 the stack is getting shorter. In the spring-loaded thing, it tends to keep it, at the same height, for customers. So push and pop, and then the same is empty in size. So those are basic operations that are available to us. I have a program called Simple Stack Queue that I wanted to show you first. This will be on the calendar for today. So I set up an array of string values, and then what I do is I make a queue of string. Notice we use the interface type for the variable, but we use linked list when we call new. With stack, we don't have a separate interface, so it's stack and stack. But so I set up a queue and a stack, and I use the simple letters Q and S for that. I have a little for each loop here that's going over my array, and it adds to the queue and pushes things on top of the stack. And then I just have some very simple code here that shows the queue initially. While the queue isn't empty, it removes something from the queue and shows you what's in the queue afterwards. Similar kind of thing for the stack. It shows you the initial one, and while it isn't empty, it pops the stack and shows you what's in the stack after that. So let's go ahead and compile, and we'll scooch this up a bit and run the program. So it sets up a queue that has the 4 and 7 years ago. It's a little hard to tell, in the bracketed notation because you don't know what's the front and what's the back. In the exam questions, you'll see this with the section problems, I always label the front and I label the back so that you'll know which is which. But I can just let you know this is the front of the queue. So we added the word for. That was the first word in that list. We added that first. So this is like the first customer in line. This is the second customer in line, the third customer. The last customer who got in line was the word ago. So since this is the stack structure, we do the removing at the front. And so, we remove the for, and then we're left with score and 7 years ago. We remove score, we remove and, etc. We don't get to this customer until the very end, which is kind of, fair, right? In that we're dealing with the customers in the order in which they got in line. Now with the stack, this is even more confusing because you just don't know what's what. So I'll let you know this is the bottom of the stack. So the very first thing is the bottom of the stack. In fact, what I do mentally is I kind of imagine taking that horizontal sequence and I imagine tilting it up so that the word for is on the bottom, and score is on top of that, and is on top of that. It's a stack of words with the word ago at the top. So I kind of turn it into that, and mentally, I turn it into that vertical thing where for is at the bottom and ago is at the top. And that's why when we go to remove something, when we pop the stack, the word ago comes off first. That's that last thing in, is the first thing that comes out. And then we get years, 7 and score and 4. We don't get the word for until the very end. So stacks have this property that when you put things into the stack and then take them back out again, you get them out in reverse order. So that's a useful thing to kind of remember about stacks, is that they have a reversing aspect to them. In the olden days, before we had all the airport security and everything, I used to arrive at the airport super late. I almost would miss the plane, and they'd just barely get my suitcase put into the cargo hold. And then when I would fly somewhere, my suitcase would be the first one to come out, which seems totally unfair, But so there's the queue we tend to associate with fairness because it does things in the order in which they were added. The stack has this property that it tends to reverse them. All right, normally I'd ask for questions. We don't have the opportunity to ask for questions, so I'll just kind of jump into what I wanted to do. I want us to write some stack queue code. So, and we're going to kind of, some of it's going to be a little dull, but, at least a few parts of it I think are going to be interesting. And it lets me mention some other issues that are important to understand. So let me begin by making a queue that's going to store integer values. So we use the interface type queue, and you'd think that you want queue of int, but remember, we'll think of it as being a queue of int, but we're not allowed to use int. We have to use a class there. And so we use the wrapper class integer. Queue of integer queue is a new. And now remember, when you call new, that's when you use the implementation. So we'd say linked list. So that gets us an empty queue. Suppose that what I wanted to do was start an I at 0, I less than or equal to 6, I plus plus. What I want to add to the queue is I times 3. So I want to add multiples of 3 to this structure. 6 multiples of 3. It goes through 6 times, adds in multiples of 3. And then I could say system.out.println q is equal to q. Well, let's just kind of see what that does. So we can compile. And it says it cannot find the symbol q. Why can't it find q? Q is part of the built-in part of Java. Most of you remember this from 142. We need to do an import. So these structures like queue and stack and so forth are part of java.util. So we need to import java.util.star, and then it's going to recognize my types like queue. And there's my 6 multiples of 3, 3, 6, 9, etc. So that's kind of what I wanted to do. Now, I wanted to, as an example, make a method for this. So I want to have a public method, public static method. I don't know what its return type is going to be for making a queue of multiples. So that's a long name, but it's very descriptive. So suppose I want a method that will make a queue of multiples where I give it a count and I give it an n. So I'd say like 6 multiples of 3. And I could, obviously I'd want to have a comment that talks about those parameters and what they mean. So what I have in mind then is that these lines of code that are here in main, I'm trying to move them into a method, to make a method out of this. Now, something that comes up here, and this is going to be something that we're going to see in several of the things we're going to talk about in the lecture today. This is a kind of review. It's that there's an issue of what's known as reference semantics. And so I'm going to point it out whenever it comes up in the lecture today, the reference semantics. And if any of this is unclear to you, this is a good thing for you to review. There's a section in Chapter 7 about reference semantics. You could go to a TA's office hours, ask some questions about reference semantics, practice it, has problems. You can look up reference semantics problems. So anyway, there's several things I'm going to be talking about today that in order to understand what I'm saying, you have to kind of understand the reference semantics. So if the idea is that this method is the one that's going to construct this list, then one of the things that I'm very clear about in 142, so I'll repeat the idea about it here, is that when you call new, you're making a request to the class to construct an object for you, and it returns a reference to that object. We can think of references in lots of different ways. I tend to draw an arrow. A reference is an arrow, is what I do in the textbook. Some people think of it as a memory address. That's not a bad way of thinking about it. Another way of thinking about it that actually kind of matches what the people who popularized object-oriented programming like to think about is they like to think about objects as conversing with each other, talking to each other. So a cell phone is kind of, and with phone numbers, is an interesting way of thinking about references. Is that what do you have stored in your cell phone? If you have someone's phone number, you have some data, some information that allows you to contact that person. So contact information, phone number. That's another way of thinking of what a reference is. When I call linked list, the linked list class, sometimes we use the analogy that it's like a factory. We call up the factory and say, make us a brand new linked list, which it returns a reference to us. And I'm storing that reference in this variable q. Because I'm constructing this inside the method, then main isn't going to have a way of knowing how to get in touch with this queue. It's not going to have access to that reference in general, because it was set up here. So when you construct an object in a method like this, what we have to do to be able to let main know how that reference, how to get in touch with that object, is that we're going to have to return it. So the return type here is going to be, we want to use the interface q of integer. Q of integer is the return type, and that means that up here in main, I can kind of replace all of that code that I had by saying make q of multiples, 6 multiples of 3. So that's how I would set this thing up. Because this method is the one that constructed the object, it has to return a reference to it if main wants to be able to refer to the same object. Okay, so are we done? Our make q of multiples is kind of is done. Normally, if you ask in the class, it would be nice to have, people spot things. I mean, this kind of it's going to give me the same output, but only because I kind of wanted 6 and 3, and this is using 6 and 3. But we don't want to use those specific values. We'd want to say count number of times, and we'd want to do n if we wanted this to be really a general purpose method that could do any count and any n. But let's try running it and see if it's still giving us our 6 multiples of 3. And it is, so that's good. All right, so that's the first method that I wanted to mention. I want to then have a stack object. Let me do this. I'm going to throw in a little println here, blank line. I'm going to do several little segments of code in main. And so we'll do a little blank line to separate them. So I want to make a stack of integer as well, and we don't have a separate interface type, so it's stack on both sides. We can still use the diamond operator. So I want to set up a stack, and then I want to write a method that I'm going to call q2stack that takes a reference to the queue and a reference to the stack, and I want it to transfer everything from the queue into the stack. So that's the idea, is move the things from the queue into the stack, and we'll see what's in it afterwards. We'll say after q2stack, let's see what's true. We'll do system.out.println, maybe throw in a few spaces, so q equals q, system.out.println. S is equal to S, oops, and hey, how about if we throw in another blank line just to kind of separate these different little bits of code that we're writing here. So we're setting up our queue of multiples here, and here we're going to do our method q2stack. That's what we want to do, is write q2stack. Let's write that method. Public static, I don't know what its return type is, q2stack, that takes a reference to a queue of integer, a reference to a stack of integer, and I want to write code that will move things from the queue into the stack. So how do we do that? Well, we can use some kind of a while loop. I'm going to just write some pseudocode for right now. I'll say while the queue is not empty, that's a way of saying that there's something left to process, right? Well, let's take something out of the queue. I'm going to say int n is q dot, and how do you take things out of a queue structure? You say remove. And then I'm going to put it into the stack. So how do you add things to a stack structure? You push onto a stack. So we'd say s dot push that n. So that's kind of what I want to do as long as the queue is not empty. I usually have a student at this point who will raise their hand and say, but couldn't you just say s.push of q.remove and do it all in one line of code? The answer is yes. In fact, that's what I would tend to do. I tend to write it as one line of code. And you'll see this, that often on exam questions, there's a need to do this, to kind of move something from a queue to the stack. And I always write it this way, in the one-line way. So yes, that's perfectly fine to write it the one way. I wanted to show you the two-line version to make clear what the two steps are. And we're going to do something different in a second where I'm going to want to do something more like this, int n. So there's reasons why I wanted to kind of show you the other version. But this is perfectly fine version to use. And it's the one that I tend to use more often. So how do we know the queue isn't empty? Well, there was this very convenient method, isEmpty, that we can use. So oops, that's not where I wanted to be. I wanted to be back over here with this file. So the queue class, the queue interface, has a method known as isEmpty. So I can say while queue is empty, but I don't want to know while it's empty. I want to know while it's not empty. So how do I do that? Well, I could say, so I want to know, I want to keep going while the queue.empty is returning false, because that would mean that it's not empty. So do I want to see whether this equals false, whether what queue.empty is returning is equal to false? That actually would work. I mean, it would do the right testing that we'd want to do, but it's a style error. This is a Boolean Zen error, so I hope some of you recognize that. Let me tell you something that could be worth writing down. You will never, ever have the need to write down equals false. Never, ever, ever write equals false, because you don't need to. Java gives us a negation operator, and I had used that in my little simple stack cube program that I was using the negation operator there. So what you want to say is while it's not the case that queue is empty, it's the reverse understanding. So the Boolean Zen way to do it, the full credit, good style way to do it, is to use the negation operator. You can always put that negation in front of something. You don't need to test whether it equals false. Well, let's see what happens when I compile this. Oh, I didn't have the return type. So there's this question, what should be returned? Well, I am emptying out the queue and filling up the stack. It kind of seems like I need to remember something later, so maybe I need to return something from this method. But it turns out that I don't need to return anything. This is a case where both structures have been constructed before the method is called. So someone else constructed the queue, someone else constructed the stack, and it was main in this case, constructed those two structures, and it already knows how to contact them. In fact, that's what main is giving us. Main is giving us a reference to the queue and giving us a reference to the stack, so it already knows those references, so it doesn't need us to return those references. And reference semantics says that as long as I have references to those existing objects, I can change their state. I can empty out the queue and fill up the stack, even though I'm going to make this a void method. So that's a little different than the early 142 programs where we had to return things in order to be able to remember a change later on. Here, we're making a change to the queue and a change to the stack that is remembered later on, because as long as we can contact the stack and the queue, we can change their state. We can tell the queue to remove all of those different values from the structure and tell the stack to add them into the structure. So there's our initial 6 multiples. And then after the call on queue to stack, the queue is empty and the stack has those. And remember, this is the bottom of the stack. So 3 is on the bottom of the stack. So that's good. That's what we were looking for. Okay. I wanted to throw in here system.out.println sum of q is equal to, I want us to write a method called sum that finds the sum of a q. And I'm going to say after sum, q is equal to q. I want to just kind of make sure, see what's in this q after we call the sum method. So how do we write the sum method? I'll give myself a little more space here. I want to write a public static method. It's computing the sum of all those integers, so the sum is going to be an int. So the sum of the things that are in a queue of integer that we could call q. I hope that you guys remember or would be familiar with a pattern that we discussed in the 142 class, which is cumulative sum. If not, you could look up cumulative sum, but it's a pretty well-known pattern. That we would start a sum at 0. We'd have some kind of a loop where inside the loop we say sum equals the old sum plus something new, and then we use the sum after the loop. That's the basic cumulative sum pattern that's described in the earlier chapters of the book. So how are we going to do this? What kind of a loop are we going to do? Well, a lot of possibilities. We wrote a loop here that kind of went through everything in a queue. How about if we just kind of copy that approach? And we say, while not q dot is empty, and then inside of here, we're going to say int n equals q dot remove, and sum gets sum plus n. So how about if we just kind of stole the idea that we were using here to find our sum? And what do we want to do to use our sum? In this case, we'd return it, because this one is just computing the sum and letting other parts of the program decide what to do with that. In this case, main is using it to print. So that would be a way to do it. Let's go ahead and hit compile and run and see what we end up with. And it discovers that the sum is 63. You could add it up and you'd find that's correct. But look at what's in the queue afterwards. It's empty. So there's a question, is that okay? It was okay in the case of queue to stack because that was the intent. The intent was that the queue would be emptied and that it would all be added into the stack. So there, that was what we wanted to do. But that's not what we want to do here. We're trying to find the sum, and there's no reason that in finding the sum you should destroy the queue. I try to be careful when I give questions on exams that I'll say things like you're not allowed to change this parameter, but it should just kind of be understood. I mean, imagine there was some place in town that they were willing to do an analysis of your car and let you know how many years of life are left on this car, or kind of what is it in good shape or whatever. So you say, they're charging $25 for this service. Sounds good. I take my car there, drop it off, and I go later in the day, and they give me my report. It's got 5 more years of life on it. Here's various issues about the car, and I say, great. Where's the car? Well, it's that pile of rubble over there. What do you mean? A pile of rubble? Well, you didn't say that we can't destroy your car. In general, when we do something like this, we expect that you're not going to destroy something unless it was something like queue to stack, where that was the intent, was that it should be emptied. So we don't want to actually empty out the queue. So what do we do instead? I usually get a suggestion from students to make a copy. And they suggest to make a copy doing something like this. Q of integer copy equals Q. So let's copy the Q before we do this loop. And then after the loop, let's say Q gets reassigned to be the copy. We'll put it back. So we'll make a copy, do the sum, and then put it back. And it's really useful to understand that this doesn't work. This doesn't make a copy of the Q. And again, it relates to reference semantics. So again, if these reference semantics things are confusing, it's something you should put a little time into studying. What does this do? This makes a copy of the reference, but not a copy of the structure. So that would be an extra, it would just be remembering how to talk to the queue. But the queue still gets destroyed. So this doesn't work, and it doesn't work because of reference semantics. Well, so what could we do instead? And I usually get people who kind of say, well, look, if I remove something from the queue to add it into my sum, what if I put that thing back at the end of the queue? I kind of cycled it from the front to the back. So after I add it into my sum, I add it back into my queue. I remove from the front and then put it back at the end. Remove from the front, put it back at the end. Remove from the front and put it back at the end. This is a very common approach that's used for solving queue problems, is you rotate the queue. Now, if you do it this way, the queue is never going to become empty. What's going to happen is the queue will always be of the same size because we keep putting things back in. So this is actually a case where a for loop is appropriate. For int I equals 0, I less than the queue's size, I plus plus, we want to do this. And if we do it, size number of times, it should rotate through the sequence of values once. And it should restore the queue to the state that it was in before. And so we end up with our 63, but we've got our sequence back again. So again, there'll be examples of this in the section problems. But this is, cycling through a queue is a strategy you should be familiar with. All right, I want to go here. I want to take all of this code we wrote here, and I want to use the last bit of class here to do some variations of this. So I'm going to want to have my stack. I already have a variable for the stack, but instead of making a queue of multiples, I'm going to want to make a stack of multiples. And then we can report what S is here, and then we're going to want to report the sum of the stack, and we'll do sum of stack here, and after sum, we'll see what the stack is equal to. I'm going to actually comment out those two lines for right now because I'm not going to do the sum initially. We don't need to be constructing something brand new here. And I'm going to make stack to q, and instead of going in that order, I'll do the other order. And I'll say after stack to q, we can see what's in the two structures. So I want to make a version of this that works on stacks. Now, we've been talking about the idea of overloading, where you use the same name twice. But here, the parameters are the same, and so we can't use the same name twice. We're going to want to return a stack of integer, and the return type is not part of the signature. So we can't use overloading here. We really do need two names. Make a stack of multiples. So we could make a stack of integer s that we set. Oops, that's not what I wanted to do. Don't know why I think it put me into two window mode. Okay, we wanted to make a stack of integer s, which is a new stack. And you don't add to a stack, you push on a stack. And then we would return that. And I want to do a variation on this queue to stack. So the variation is going to be called stack to queue. And I think that when you're doing it that way, it's kind of nicer to reverse the order of the parameters, where we have stack of integer s, and then the queue of integer as the second parameter. And so we can just kind of do a simple translation here. While the stack isn't empty, we will do, you don't remove from a stack. What do? You pop a stack. And you don't, we were trying to move over to the queue. You don't push onto a queue. You add to a queue. And the kind of the equivalent of that then becomes a q.add s.pop would be kind of the one-line version that's like what we had before. I wasn't intending to introduce any little errors there. Ooh, I misspelled stack. So let's fix that. Probably some of you guys noticed that error. And let's go ahead and run it. And so what it does is it makes a stack of the 6 multiples, and after it calls Q to stack to Q, the stack is empty and these things have been moved into the queue. Notice they're in reverse order. That's that reversing aspect of the stack. So that's what we wanted. Those two worked out fairly nicely. Now, what I want to do next, though, is I want to do the sum part. Now, sum is something where we can use overloading. We can use the same name for the method because the parameters are going to be different. So we had something called sum that was taking a Q, but we can have a second method called sum as long as it takes something of a different type, and we're going to make it a stack of integer s. So we'll go nest in stack size. You don't remove from a queue. You pop a stack. You don't add it back in. You push. So that's kind of the simple translation for our sum method working with a stack. Let's do a compile and run. And let's see if we've got our let me scooch this up a little bit to see a little more. And you can see that it computed a sum of 63. Well, maybe it didn't compute a sum of 63. Why not? It didn't work. Why did it compute a sum of 108? Well, stacks or queues are different, and this is a case where that difference matters. So what are we doing? The stack has in it these values. When we pop it, we get an 18. And we add that into our sum, and then we push 18 back on the top of the stack. But then what happens when we come around again and we pop? We get 18 again. So basically what we're getting here is 18, 18, 18, 18. We add 18 to our sum 6 different times, and that's not what we want to do. So this is a case where we really do want a second structure, which would be convenient. If I was going to give you a second structure, is it more convenient to have a stack or more convenient to have a queue? I swear, people always say queue, which is the wrong answer. It's more convenient to have a stack. But a lot of people, I'll have someone in the front row who says use a queue, and I'll say, well, okay, it would have been easier to use a stack, but it's your fault we're going to use a queue. Actually, I want you to solve it in the harder way because it makes it a more interesting problem, a more challenging problem, that I kind of give you the wrong data structure to work with. So I'm going to give you a queue. You pop the stack, add it in, and so then we're going to kind of use the queue as the way to remember the things that we've processed. So we'll move them from the stack to the queue, and then at the end, things are going to be in the queue that need to go back to the stack. How do you do that? How do you move things from a queue to a stack? Well, we have a method, queue to stack, that would move them from the queue back to the stack. So let's compile and run that version, and let's see if we've got our sum of 63, which we don't have. And let's see if we restored the stack the way it's supposed to be. Well, it begins with 3, 6, 9 like it did before, but then it has 18, 15, 12. There are 2 distinct bugs here, both of which are important to understand. 2 things going wrong. So here's one of them. We were using this for loop here. So think of what's happening though. The stack initially has a size of 6 and I is 0. And then we remove something from the stack, so the size becomes 5, I becomes 1, the size becomes 4, I becomes 2, the size becomes 3, and I becomes 3. So the size is going down as I is going up, and halfway they meet. So this is not going to execute the proper number of times. If we wanted to, we could do the following trick, which is a common trick that's good to know about. We could say old size equals stack.size, and then we could use the original size. We could use old size here. So if you really wanted to use a for loop like this, that would be the way to do it, is by remembering the size before you begin the loop. So that would be a way to do it, but we can actually do it in an even easier way, which is just to say, while it's not the case that the stack is empty. We know we want to do the whole thing. So while the stack isn't empty, we can just process the whole thing. And if we do compile and run, we'll find that now it gets the 63, but it reverses things. Because remember, stacks reverse things. It would have been in the proper order if our temporary structure was a stack. But this means it's in reverse order. How do we get it into the original order? Well, we just do it again. We do stack to queue, stack to queue, and we do queue to stack. We just do it again. And I think I'm probably about to get cut off, but I'll post it for today. We may have just enough time to see that it got the 63 and it restored the stack. So an extra time of doing stack to queue, queue to stack fixes the second bug, which is the things being in reverse order. All right, we'll do more on Friday.